So this is our moment of inertia example. Now let's say again we've got a cross, like so. Let's now put numbers to this. Let's say we've got 1 kilogram masses everywhere. And let's say all of them are 1 meter away from the point of rotation. So that is our point of rotation. And the rotation is in the plane of this page. So this cross is going to rotate on this flat surface, round and round. Let's just, for argument's sake, say it's rotating counterclockwise. And we now need to calculate the moment of inertia of this object. So remember, we said the moment of inertia is equals to the sum of masses times how far they are from the axis of rotation squared. So this is just a mass. This is how far that mass is from the rotation axis. In this case, the rotation axis sticking out of the page given by my pen. So this cross rotates around that axis. We can calculate the sum. There are going to be 4 masses. Each one of them is 1 meter away. So this means the moment of inertia is mass 1. We can take as 1 kilogram. It's 1 meter away from the axis of rotation. Plus, same for the second one, 1 kilogram being 1 meter away squared. Third one is again 1 kilogram. It's 1 meter away squared from the axis of rotation. Plus the last one, 1 kg, 1 meter away from the axis of rotation, square that. So this is 1, 1, 1, 1. So we get the moment of inertia, in this case it's going to be equals to 4 kilograms meter squared. So just note that's the units of the moment of inertia, kilogram meter squared. Okay, so that was quite simple. But now let's change things a bit. Let's say now the cross rotates in a different way. So if this is our cross, instead of it rotating in this plane like that, it now rotates around its own vertical axis. So it now rotates like so. So if this was the cross, we had that it rotated like this. Now we say it's going to rotate around a different axis like so. So this is a different rotational axis. Now the moment of inertia becomes different, because remember the moment of inertia is how much mass we've got, how far away from the axis of rotation. So now we've got 2 masses that are each 1 meter away from the axis of rotation, but we've got 2 masses which are on the axis of rotation. Same with that one, it's on axis of rotation. So now my moment of inertia, I start with that one, it's the mass 1 kilogram times how far it is from the axis of rotation. That one is 1 kilogram, but it's on the axis of rotation, so it's got no separation from the axis of rotation, so that is a 0. There we go. Plus that mass is 1 kilogram, and it's also 1 meter away from the axis of rotation. Plus that mass, it lies on the axis of rotation, so it's 1 kilogram, and it's 0 meters away from the axis of rotation. So we get that the moment of inertia now is simply 2 kilograms meters squared. So note that the same object, if it changes its axis of rotation, its moment of inertia will change as well. So for example, a rectangle rotating about its center will have a moment of inertia of some value. If it rotates like a door around a hinge, it will have a different moment of inertia because the mass is now distributed differently around the axis of rotation. Otherwise, you can think of moment of inertia as being the rotational analog of mass. You'll see tomorrow that, like we had when we did straight line motion, if I've got a certain applied force giving me a certain acceleration, the larger the mass is, the less acceleration I get for the same amount of force. We will see the same thing with moment of inertia. If I've got a force that rotates an object, you'll see that is actually a torque. We get a certain angular acceleration out, and the larger the moment of inertia is, the smaller the angular acceleration is for a set of applied forces. Thanks, we'll continue with that tomorrow.